Good afternoon, everyone. So we will start our discussion on the week 12 content for the NPTEL course of Power System Engineering. So I am your course TA, Adyasha Sahoo from IIT Roorkee. So first we'll see a brief overview or the concepts that we will be using for solving the assignment. So for this week, we will be seeing the low frequency control of two area interconnected power system. So let us see that. So, of so this two area concept can be also easily extended to multi-area interconnected systems. So for simplicity, we'll start with a two area. So let's say this is your first area, area 1, connected at this bus 1, and this is the tie line connecting it with the other area, that is area 2. So both these areas, area 1 and area 2, they are connected by this tie line, and we assume that this is perfectly reactive. We assume that the resistance of this tie line is neglected, basically R12 is taken as 0, and let's say the power flow direction or current flow direction is from area 1 to 2, which is represented by I12, and let the voltage of this bus 1 be V1 at an angle delta 1, that is V1 magnitude angle delta 1, and the area 2 be connected at a bus with voltage magnitude V2 and angle delta 2. So and let us say that the power that is being injected here at this bus 1 here, so let this be your initial power P tie 1 to naught plus JQ tie 1 to naught. So we know that the formula for your injected power, that S12 is your VI I12 conjugate, right? So if I take the conjugate of this, so S12 conjugate will be V1 conjugate and I12. So what will be S12 conjugate? Basically S12 is your P plus JQ, so its conjugate will be P minus JQ. So P tie 1 to naught minus JQ tie 1 to naught. So that is equal to your V1 conjugate I12. So let us now replace this V1, sorry, in place of this I12. So I12 we can put here it as, basically what will be I12? Difference between the voltage at bus 1 and bus 2 divided by the reactance of this line. So difference in voltage is basically V1 delta 1 minus V2 delta 2 divided by the reactance, that is your JX12. So now multiplying this basically, so here what you'll get, V1 into V1, basically it will be V1 square magnitude square minus, so this V1 conjugate, it will be basically magnitude and angle will be minus delta 1, right? So multiplying that, that will give us V1 V2 into angle of delta 2 minus delta 1. So let these initial angles be represented by delta 1 naught and delta 2 naught. So here also you'll get delta 1 naught, delta 2 naught divided by JX12. Now let us multiply. If we multiply basically j and the numerator and denominator, so you will be getting j v1 square. So before that, let us split this angle, because this will be also have real and reactive part, right? So before multiplying that, so let me first expand this angle part. So v1 square minus v1 v2, and this will be cos plus j sine, right? So cos delta 2 naught minus delta 1 naught plus j sine delta 2 naught minus delta 1 naught divided by jx12. So after this, if I basically multiply with j, so what I'll get here is basically j times, and j will come in here first, this v1 square, and basically this real part, that is v1 v2 cos part delta 2 minus delta 1 naught. So this is your terms coming with j, and without j it will be basically minus j into j will be minus j square, which will be plus j square is minus 1, so it will be plus v1 v2 sine delta 2 naught minus delta 1 naught divided by, so this will be j square is minus, so minus x12. So in the left hand side we had p tie 12 naught minus j q tie 12 naught. So if you compare the real parts and the imaginary parts, from here you can finally get your from here you can get p tie 12 naught, which will be basically real part of the right hand side equation. So that will give us minus, if I take into the sign, because sign of minus delta is minus sine delta, right? So basically that will be v1 v2 sine of delta 1 minus delta 2, because we are taking the minus of the denominator here, and x12. So that is our expression for the power flow through the tie line between area 1 and area 2. So after this, so whenever there is a change in load, so whenever load changes, so it will lead to, we know, some change in frequency, right? So that will lead to change in frequency, and we have seen earlier, right, that decoupled equations of the power, that P is directly proportional to your F, and that will affect only the voltage angle part, not the magnitude. So if the frequency changes, the angle will change, and reactive is basically related to your voltage magnitude. So here frequency is changing means only the angles will change, the magnitude will not change. So there will be change in angles, that is your delta 1 naught and delta 2 naught, whereas your V1 and V2, they are fixed, or they will remain same as previous. So we have seen the expression for p tie 12. So if the delta 12 will change, so p tie 12 will also change. So this will lead to change in the tie line power flow. So let's say there is some delta change in the angles and delta change in the Thailand power flow. So let the new delta be delta 1 naught plus the change delta 1 delta 1, and the new angle delta 2 at bus 2 is delta 2 naught initial plus the change in angle delta 2, and similarly let the new power flow through the tie line be p tie 1 2, which is p tie 1 2 naught plus delta p tie 1 2. So again, so if I basically write that, so p tie 1 2, so instead of naught I have this total p tie 1 2. What will be it? Basically first is basically p tie 1 2 is your v1 v2 by x12 sine of this new angle delta 1 minus new angle delta 2. So we'll substitute these values. So I'll get v1 v2, they are fixed, line reactance will also not change, but sine of basically delta 1 plus del delta 1 minus delta 2 minus of del delta 2. So here again if I rearrange those terms, what I'll be getting is sine of delta 1 minus delta 2 plus del delta 1 minus del delta 2, right? This is plus. Now we know that this sin A plus B will be sin A cos B plus cos A sin B. So basically sin is not sin A cos B plus cos A sin B. Now we'll do some approximations. So basically if we take that this delta 1 and delta 2 are small, so we know that, so basically that the difference will be further smaller. So cos delta 1 minus delta 2 will be nearly equal to 1, and sin delta 1 minus delta 2 will be delta 1 minus delta 2. So substituting that, so v1 v2 x12 sine of delta 1 naught minus delta 2 naught, cos will be 1 plus cos of delta 1 naught minus delta 2 naught, and this will be delta 1 minus delta 2. So if I multiply this v1 v2 into x12, so this first term, that will be nothing but your p tie 1 2 naught plus this additional term will come, that is v1 v2 x12 cos delta 1 naught minus delta 2 naught into delta 1 minus delta 2. So basically this will cancel out, and So this will cancel out, and basically your beta 1 2 will be this expression for your change in power flow through tie line 1 2 whenever there is a change in load in area 1 and area 2. Now if we write that in per unit, so let that rated power be PR1. So basically delta P tie 1 2 divided by PR1 will be V1 V2 by PR1 X12 cos of delta 1 naught minus delta 2 naught into del delta 1 minus del delta 2. So in per unit, delta P tie 1 2 in per unit will be this T12 into del delta 1 minus del delta 2, where your this T12 will be nothing but V1 V2 cos delta 1 naught minus delta 2 naught divided by PR1 X12. Okay, so if we write this in terms of change in frequency instead of change in angle, so basically this beta 1 2 will be we have seen it, right? 2 pi f will come. So you know that, right? Because your d delta by dt is 2 pi f. So for small changes, we can write that when there is small, so del delta is same as your d delta. So that will be 2 pi change in angle delta f, right? So that is, if we integrate again to get del delta 1, so that will be 2 pi integral of del delta f dt. So here same, if I replace del delta 1 by this integral change in frequency f1 dt minus change in frequency delta f2 dt. Similarly for 2 1, I can write it as 2 pi t21 delta f2 dt minus delta f1 dt. Now if we divide these two equations, beta 1 2 by beta 21, that will give us t12 by t21, but a negative sign will come because here delta f1 minus f2, here f2 minus f1, so minus. And if I take this basically t21, what it will be? It will be v1 v2 cos delta 1 minus delta 2 naught divided by pr2 x12. So basically this will be cos delta 2 naught minus delta 2 1, delta 2 minus delta 1, but we know cos of minus delta is same as cos delta. So here basically if I divide these two, so I will be getting minus PR2 by PR1. So that we represent by this ratio A12, basically 1 by A12, where your A12 is nothing but ratio of the area capacity, respective capacity, right? So A12 is ratio of capacity of area 1 divided by ratio, so basically capacity of area 2 with a negative sign. So from here I can tell that p two 1 is A12 times delta p 12. Okay. So basically, if you remember this, or let me draw. So this is your area 1, this is your bus 1. So this is your p 12. So, and here you have a load PL1, and here you are injecting power PG1, right? So this power balance equation, basically if I write in this under transient conditions, so under transient disturbance, so similarly I can write the incremental power balance equation. So that will be nothing but your change in generation PG1 minus PL1 change minus change in Thailand power flow delta PT12. So that will be nothing but we had seen 2H by F naught. So d by dt of delta F plus d1 delta F1. Right. So if I take the Laplace of this equation, so taking Laplace of above, so from here basically I can find your delta F1 as delta Pg1 minus delta PL1 minus delta P12 into Kp1 divided by 1 plus STP1. Just a second. Hello? ନାଇଁ ଫୋନ୍ କରିନି ମୁଁ ଭାବିଥିଲି ତମେ ସେ ପାଇଁ ଫୋନ୍ କରିଛ ଏବେ ହଉ ଫୋନ୍ କରୁଛ ହଁ ହଉ ହଉ ହଁ ମୁଁ କ୍ଲାସ୍ ନଉଛି ହୁଁ 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 yes so this was this here we had seen earlier, right? Kp1 was 1 by d1 and Tp1 was 2h by d1 f naught. So this one be, let's say, h1, so 2h1 by d1 f naught. So here if I draw the block diagram for this, so here we have a summation, so positive pg minus pl1 pg1 and minus p12 and multiplied by this kp1 1 plus st1 will give us the change in frequency delta f1. So that is for area 1 and this is for area 1, and similarly we can do for area 2, right? So summation Pg2 minus PL2 minus delta beta 2 1 will come here, right? Or you can write it as A12 delta, or let me just write it in terms of P12 only. So here A12, here I have delta beta 12 here also, and that will be multiplied by Kp2 1 plus Stp2, that will give me delta F2. And this is for area 1, this is for area 2, and similarly for basically tie line, if I do, so I'll draw it here, let's say. So delta p tie 1 2, this one basically, if I take the Laplace here and do it, so it will be nothing but 2 pi t12 by s from this basically integration sign. So this will be delta f1 minus delta f2. So its block diagram will be like, so delta f1 minus delta f2 into this one 2 pi t12 s will give us delta p tie 12. So basically these three, if we integrate, so that will give us the final model for this two area system. So basically you see, this is area 1, so governor turbine reheat we have not considered here. So this one governor turbine, and then you have your delta pg1 minus pl1 minus p tie 12. So this is p tie 12 into kp1 by 1 plus st1 was delta f1. This one, if you remember, right? This was p tie 12. So p tie 12 is coming from here. That is giving you f1. Similarly, for second one, it is same for second turbine, governor turbine, and delta pg2 is here minus delta pl2. So minus p tie, basically a12. So here this is nothing but a12 into delta p tie 12, which is your same as delta p tie 21. So minus that, if you see here, so this part, this lower part here, so that is coming here pg2 minus pl2 minus p tie 21 multiplied by this kp2 1 plus stp2 is giving you delta f2. And earlier we have seen this feedback from delta f1 and delta f2 through 1 by r1, right, and 1 by r2, that is coming here. So area 1 and area 2, and this is the between these two, area 1 and area 2, you have the tie line model, right? So for tie line we had this one delta f minus delta f2 multiplied by 2 pi t1 to s. So if you see here delta f1, so this is delta f1 minus delta f2 multiplied by this 2 pi t1 s2 is giving you p tie 12. So I hope this was clear. Now let us check mathematically what will be the value of this. So First, let us consider the uncontrolled operation, so that your u1 and u2 are 0. So under such condition, the steady state frequency deviation will be same for both the areas, right? So the steady state frequency deviation is same for both areas. So that is your delta f1 is same as delta f2 is same as your delta f steady state. So again, if I write the incremental or transient incremental power maintenance under transient conditions, so what I'll be getting is delta Pg1 SS minus P tie 12 SS minus PL1 is your T1 delta F SS, right? Because in this was for under transient disturbance, right? So this basically D part will be not there in steady state. This is we are considering steady state. So basically your d by dt delta f, that will be 0 in steady state. So hence from this equation, basically this part will go out, this 2h1 f d by dt of delta f, and in steady state only d1 will be there. Similarly for area 2, it is pg2 ss minus, let's say, a12 p tie 12 ss minus pl2 is your d2 delta f steady state. And we have also seen from that isolated area case also, delta Pg1 steady state is nothing but minus delta F by R1, and Pg2 steady state will be minus delta F steady state by R2. So if I substitute those value in this equation 1 and 2, and additionally if I multiply equation 1 with a12, so what I'll get a12, so that will be minus delta fss r1 minus a12 delta p tie 12 ss minus a12 delta pl1 equal to d1 a12 delta fss, and second equation as it is. So or into minus 1, let's say, so that will be delta fss by r2 plus a12 delta p tie 12 ss plus pl2 equal to minus d2 delta f steady state, right? And then let me add these two equations, so these two will cancel out, and what you will get as delta f steady state, so you'll get a12 delta pl1 minus pl2 divided by basically coefficients like D2, and here I'll get 1 by R2, and here I'll be getting minus D1, or let me take common, so minus A1 to D1 minus R1, so plus 1 by R1. So that is you are getting for delta FSS. Similarly, if you put this in equation 1 or equation 2, you can get for the value of steady state value of change in power flow through tie line 1 2. So that expression, let me write. So if you put that, or let me write it in the next slide, delta p tie 1 to steady state, you will get as d1 plus 1 by r1 delta pl2 minus d2 plus 1 by r1 delta pl1 divided by the same thing, d2 plus 1 by r2 minus a1 to d1 plus 1 by r1. So there a special condition or case, let's say when the rate or capacity of both areas are same rated capacity, that is PR1 equal to PR2, then your A12 will be minus 1, and let's say the D is 0 and R for both the areas are same. So under such a condition, your delta F steady state will be basically, if you see in this expression, so D is 0 and here delta PL2 is also 0, so that is disturbance only in area 1. So PL2 is 0, that will go out, D has gone, so A12 is minus, so that will be minus delta PL1 divided by D2 minus D2 plus D1. No, D is not there, 1 by R2 plus 1 by R1, or basically here only R, because both those are same. So that will give us minus R into delta PL1 by 2. And what about your change in tie line power? So here also PL2 is 0, PL1 D is 0, so minus 1 by R delta PL1 divided by 1 by R plus 1 by R. So that will be minus delta PL1 by 2. So this is for a special case for this condition. Now next is your frequency bias controller, that is your supplementary control. So tie line frequency bias control. right? So this is popularly known as also supplementary control. So this is after your primary control or on top of your primary control. So its objective is basically that this supplementary control should respond or control or regulate whatever the frequency or load deviations or changes in its own area. So that means that in whenever there is a change in or disturbance in area 1, so only the supplementary control action of area 1 should be activated. Area 2 should not respond for changes in area 1. So that is its main objective. So it should respond only whenever or only to correct the deviation in its own area, within its area. It should not respond to changes out of its control area. So that we achieve by adding a bias here B1, which we generally say. So for this area control error 1, that will be B1 into change in frequency in area 1. So above this, we always have tie12 also. And for area 2, similarly B2 change in frequency delta F2 plus A12 delta P tie12. So here B1 is nothing but your same as your frequency response characteristics of your area 1 and 2. So that is D1 plus 1 by R1 and B2 is beta 2 D2 plus 1 by R2. So basically what we do, we will add a integral controller which will make this area control ACE to 0. So if I do the block diagram, basically I'll be having P tie12 plus this is your B1 delta F1. So B1 delta F1 plus P tie12 will give you your ACE1, and this area control error should be minimized by your integral controller minus K1 by S, and that will be your U1. And similarly for area 2, this is your area 1. So that is nothing but here additionally you will have A12 delta P tie12 B2 delta F2, that gives you ACE2 minus K2 by S, that will give you U2. So basically in this diagram, so this is your delta F1, right? So above delta F1 again you will have B1, and before this I'll have an integral controller minus Ki by S, and this is your P tie12, right? So I'll add summations here. So basically this is your delta P tie12 plus this B1 times delta F This is your P1 delta F, right? F1. So this is your ACE1 with K1. So that is for area 1. Similarly for area 2, that will be nothing but, again, here I'll have minus K2 by S. So this is your delta P tie 21, which is same as your A12 delta P tie 12, and here I'll add bias B2 to delta F. So this is your B2 delta F2. This is your SE2. So this is the tie line frequency control diagram. So there are you will see different techniques that how to set or select the bias vector. So it should basically follow the objective. Whatever bias you select or the selected the bias B1 and B2 should be such that whenever you have disturbance PL1, so then only your AC1 should be delta PL1 and AC2 should have no, it should not respond to this disturbance because it is for area 1, it is not for area 2. Similarly, if there is a disturbance PL2, then your area control error 1 should be 0, but your second should be equal to exactly equal to your PL2. So this should be your basically for steady state. Again, if you see basically, so this one will be B1 delta F1 steady state plus A1 will add, let me write here, that will be B1 delta F steady state plus some A1 delta P tie 12 steady state, so that should be 0, and for the second area it should be B2 delta F steady state plus A2 A12 delta P tie 12 steady state should be 0. Okay, so with this, let us see the assignment questions. So for the first question, you have a two area power system connected by a tie line with the following characteristics. So R is given for both areas, D is given, and the base MVA is given. So whenever there is a 50 megawatt of load curtailment in area 1, find out the steady state frequency. So basically it is saying you have area 1, area 2, and they are connected by this tie line, and you have your load curtailment. Load curtailment means load will decrease, right? Implies a decrease in load. So decrease in load means your delta PL1 is minus how much? 50. So whenever you have delta PL1 as minus 50, and here there is no change. Nothing is given here. So delta PL2 is 0. So under such a condition, you need to find the steady state frequency. So this we had seen, right? Basically, your delta F, basically this formula, right? So let me write it here. So delta F will be A12 delta PL1 minus delta PL2 divided by D2 plus 1 by R2 minus A12 D1 plus 1 by R1. So here you see both have equal rated capacity, right? So your A12 is minus 500 by 500, that will give you minus 1. So put here A12 minus 1 and PL2 0. So you will get minus PL1 divided by D2 plus 1 by R2 plus D1 plus 1 by R1. So if I put the values, so minus of minus 50 divided by your, all are in per unit, so you can add all these. So 0.8, 1 R is 1 by 0.05 plus 1 by 0.04. So if you do this, you will get, so sorry, delta PL also you need to put in per unit, right? So delta PL1 is minus 50 megawatt, or it will be minus 50 by 500 per unit. That will give me minus 0.1 per unit. So if I substitute that, so you will get it as 0.002136 in per unit. So for hertz, what you need to do, you need to multiply by 50, right? So this multiplied by 50, that will give you 0.1068 3 hertz. So what will be your F? Steady state will be F naught plus delta F. So 50 plus this, so will be 50.10683 hertz. So that is option B. Okay. Now I think same question is there, and it is asking that regarding change in tie line power flow at steady state, assuming no control action, right? So U1, U2 is 0. So tie line, if you see the expression, so delta P tie 1 to steady state. So that was D1 plus 1 by R1 delta PL2 minus D2 plus 1 by R2 delta PL1 divided by D2 plus 1 by R2 minus A12 D1 plus 1 by R1. So here if you again put all those values, that is A12 as minus 1, delta PL2 as 0, so that will be reduced to delta P tie 1 to steady state will be PL2 is 0, so this will go out, so minus D2 plus 1 by R2 delta PL1 divided by D2 plus 1 by R2 plus D1 plus 1 by R1. So denominator is always positive, right? Because these are all, yeah. So denominator is positive. Basically delta P tie 1 to steady state is, so this is a positive quantity, minus D2 plus 1 by R2 is also positive quantity. And what about delta PL1? It is negative here, right? Delta PL1 is minus 50. So this will give that the whole will be positive. Right, I hope it is clear. So delta PA12 is positive. So this was, if you remember the direction, so this is P tie 12. So tie 12 is positive, means power flow is from area 1 to area 2. Right, additional power flow is from area 1 to area 2. So what are the options? So option is tie line power flow from area 2 to area 1 will be decreased. So if the P tie 12 is basically positive, so let's say that before P tie 12 not was some, so earlier what it was, okay, value we have not calculated. So let's say it was something 1 megawatt or something like that. And now you have got that P tie 12 is, let's say, zero point 0.2 megawatt. So what is the final P tie 12 in steady state? This is their sum, right? So 1.2 megawatt. So if there is increase in power from this tie 1 to 2, so for tie 2 to 1 it will be decreased. So right? So see the option B, tie line power flow from area 1 to area 2 will be decreased. So that is wrong, right? Because here you see delta P tie 12 is positive. So your P tie 12 will increase and P tie 21 it will decrease. There is no change in tile and power flow. No, this is wrong. We see there will be change in power flow. Cannot be ascertained. Okay. Now the next question. So same thing is asking. It is now asking what is the magnitude of change. Basically, it is asking the value here. So delta p tie 12. So we have seen that it was minus d2 plus 1 by r2 delta pl1 divided by d1 plus d2 plus 1 by r1 plus 1 by r2, right? Yes. So if I put the values here, basically minus of area 2 is 1 plus 0.04, okay, and this was minus 0.1 in per unit, right? Delta pl1 is your minus 50 megawatt or minus zero point 0.1 per unit divided by this sum. So if you do that, you will get as 1 plus, so 1 plus zero point 0.8 plus 0. So this will give you 0.0555 per unit, and what will be it in actual? You need to multiply by 500, right? So this 0.0555 into your base is 500, so you'll get 27.778 megawatt. So it is option C. Now the next question. So here it is the same question. It is asking that what is the magnitude of steady state change in mechanical power output of prime mover in area 1. Basically, it is asking delta PG1. So delta PG1, we see that it was delta F steady state minus by R1, right? So minus, so it was your steady state change in frequency. It was 0.002136, 0.002136. See, R1 is in per unit, that's why this also we are putting in per unit, right? So per unit divided by R1 is 1 by 0.005, so that you will get as 0.002136, 0.05. You'll get it as 0.00010. Just a second, 0.002136 into 0.05. Yes, so I am getting this 0.006 per unit, or into 500 if I do. Oh, okay, so I have done this one wrong here. So this is R1 only, not 1 by R1. So divided by 0.0005. So that will give you 0.02136, 0.05. That will give you minus 0.04272 in per unit. So this into 500 will be in megawatt. So that will be nothing but your minus 21.36 megawatt. So that is your option A. Now it is the same question again. So 50 megawatt curtailment low area 1. So it is asking in delta Pg2 basically. So delta Pg2 is nothing but your minus delta F steady state divided by R2. So minus 0.002136 divided by R2 is 0.04. So that gives me 0.02136 divided by. So that gives us 0.0534 per unit, or in actual it will be 0.0534 into 500 megawatt into 500. That gives me 26.7. So this is minus, right? Minus, minus 26.7 megawatt. That is option C. Now again same question is there. So it is asking what is steady state change in total load. So frequency in area 1 due to change in frequency. So it is asking you delta P load 1. So that will be your this frequency response characteristics of D1 of loads, that is D1, into delta F steady state. So D1 is your zero point 0.8 and this is your 0.002136 which is your which is your 0.001788 per unit, or 0.001788 into 500 megawatt. It is your 0.8544 megawatt. So that is your option D. Now, seventh question, it is asking that same question. It is now asking in change in load in area 2 due to this change in frequency. So PL2 is D2 times delta F steady state. D2 is 1 into 0.002136. So that is 0.002136 per unit, or 1.068 megawatt. That is option A. Okay, now another question is here. So for a three area system, a load of 10 megawatt is suddenly increased in area 1. So delta PL1 is your plus 10 megawatt, and PL2 and PL3 are 0. So generator installed in three areas and their rating are given, and the speed regulation, that is R, is given for all three generators. So neglect the friction. Find the steady state frequency deviation. So for that, so nothing. It will be just, you need to calculate the equivalent, right, of this. That will be 1 by R1 plus 1 by R2 plus 1 by R3. No D is here. That is no frequency sensitive change in load is considered. So that will give you, but here R are on different base. So let us change that first. So basically R1 is 0.08 per unit on 100 MVA. So that, let us keep us fixed. R2 is 0.06. This is not in per unit. This is percentage basically. 0.06 on 200 MVA. So if I calculate the new one, that will be R2 into new base divided by machine rating. Right. So let us, we are calculating here on a base of 100 MVA. So R2 dash will be 0.06 into 100 divided by 200. So that will be 0.03 per unit. So R3 dash will be it is 0.1 on 400 MVA. So 400, no, 100 by 400. So that gives us 0.025 per unit, and R1 will be same, right? So 0.08 into 100 by 100, that gives us 0.08 per unit. So R1 dash, R2 dash, R3 dash. So this will give us 1 by 0.08 plus 1 by 0.03 plus 1 by 0.025. So that is giving us your beta as 85.833 per unit. Now delta PL1, that is plus 10 megawatt, or plus 10 by 100, that is your 0.1 per unit. So delta F is minus delta PL1 divided by this beta, so minus 0.1 divided by 85.333, so that is giving us as minus 0.0011718 per unit, or multiply with what is the base frequency, nominal is 50, so 1178 into 50 hertz, that gives us 0.0586 hertz. So I think option A is correct here. Minus 0. No, it is minus, so option C. Okay. Now the next question. So here two interconnected areas, area 1 and area 2. So area 1 has 500 megawatt of generation and has a frequency response characteristics as 150. Area 2 has 400 megawatt generation and response characteristics is 200. So each area is initially generating one half of its total generation. Okay, and there is no tail end power flow at 50 hertz. So what happens? The load in area 2 suddenly decreases by 100 megawatt. So PL2 is minus 100 megawatt. So it is asking that determine the steady state frequency without load frequency control. Okay, so delta F steady state will be nothing but minus delta PL2 divided by 1 by R1 plus 1 by R2, or that is similarly beta 1 plus beta 2. So that is minus 100 megawatt and beta 1 is 150 plus 200 So yes, so initially what is the beta 1 is 150 megawatt per hertz, and beta 2 is 200 megawatt per hertz. So that will give us 100 divided by 150 plus, yeah, so 150 plus 200. So this is in megawatt per hertz. So this will give you 0.28571 hertz. So delta F is 50.28571 hertz. F. So 50.28 is option 1. Now next question. So here it is saying that same load in area 2 suddenly decreases by 100 megawatt. So delta PL2 is your minus 100 megawatt. Assuming load frequency control is enabled. So LFC, you have controller here. So that implies that what happened? Your controller will make the steady state error as 0, right? Because here you have LFC. So basically it is none of the above, because this will be 0 means your beta 1 2 will be also 0. So that is for this week's assignment. So besides this, we have two topics, that is your automatic generation control, AGC for deregulated power systems, and thereafter we have unit commitment. So let us discuss for this deregulated power systems today some, and we have extra class tomorrow, so there we will discuss about unit commitment. So let me add a slide here. Yes, so first we will see the traditional power system, which was your vertically integrated utility. So as you know, the power system, so it consists of three components. So at the start, you have your generators, which are your sources of energy or power in the system. So that is your generating stations or your generation. So this consists of your earlier, like there were thermal power plants, hydro, maybe nuclear or biomass, or likewise. And at the receiving end, we had the load. So that was for your distribution systems, and in the distribution system, the loads were connected. So there may be your residential loads, so there may be your residential load, there may be commercial, official, right? So this, and from the generating station to the distribution system, so the power head is transferred through your transmission system, right? Transmission lines in between we have. So this is your transmission system. So this was your, in a vertically integrated utility, the three systems, that generation, transmission, and distribution, this was owned by one single entity, which was generally the government. So why it was so? So if you think about, let's say 50, 60 years back, so at that time there were not many generators in our system, right? Mostly it was government owned thermal power plants. So uh, in the in those era, what was that? The main aim was to satisfy the load because we did not have sufficient generation during that time. So the main aim was security or security of supply, or to meet the load demands. And hence at that time all the generation, transmission, and distribution, so it was owned by a single entity. So gradually, when we had a more number of generators in the system, or when we had adequate, we can say, power that can supply the loads. So after such a condition is was arrived, when such a scenario was there, when we could satisfy our loads, we had sufficient generation in our system. So after that, we were focused upon the economics. Like now we have sufficient generation. Now we want to see that how we can supply this power to the consumer, but at lower rates or cheaper rates. So the problem in this vertically integrated society was, in utility, was that it was a type of monopoly. You can see, right? There is no chance of competition here because all are owned by single one. So you're bound to purchase from that entity only because you don't have any options for you. So let us take example. Let's say you are a buyer and you want to, let's say, buy a phone. So if you have a single uh, option to buy from, like earlier you had just BSNL, so everyone was going to BSNL, right? So that time BSNL was, we can say, it had monopoly. There was no competition. And after some years, after the development, we can say, more companies came into existence, right? Reliance came, or all those things. So now what you had options to choose from, right? There was BSNL, there was Reliance, there was Airtel. Now, when the user is having options, you will mostly go to that system which will give you the services at lower price, right? Now, you don't care whether it is government or whether it is private. You want that the price should be low. So similarly, when the after some years, when the generation system was basically evolved, we can say. So and there, uh, and competition, another thing, it is always required in the system, right? Because when there will be system, then only you can say that the companies will try to change, right? Because if you don't have a competition, you don't need to like enhance the quality of your goods. Whatever price you tell, they have to take because you're having monopoly. But once you have a competitor, now I'm telling the point of view of a generation generator, let's say. So if I'm a single generator in the system, so I will not care like what is the price at which I am producing the power. If it is 5 rupees per megawatt also, I will sell it because I don't have a competition with me. But as soon as my competition enters in the market, and let's say it starts selling its power at 4 rupees per megawatt. So now automatically the consumers, they will go and buy power from my rival at 4 because he's selling at lower price. So what now I will try to do, I will try to optimize my cost such that I will also try to bring my price to 4 rupees per megawatt. So for that, it will lead to innovation. So the generation companies, they will try to like they will what you can say, they will invest in such you can say factories or machineries which will be more efficient, so that their cost of production uh, decreases. So when their cost of production will decrease, then obviously they can have greater profits, or they can sell power at lower price. So that thinking, that way the generator company will only go when it will have a competition. If it is not having competition, it will no it will have do not have any incentive to improve its quality, or to reduce its price, right? So hence, to bring this uh, basically competition and to the system, so we it was suggested that we tried unbundling this system. So basically, we suggested that now instead of having a monopoly in a system, so anyone, so this is distribution system. This is your instead of one company, we have now your multiple generating companies: G1, G2, G3, G4, G5. So they were known as your Gencos, or your generating companies. And similarly, in the distribution side, we had the Discos, or the distribution companies, and we had Transco. So apart from this, we had some industrial loads also. So industrial loads, they directly can connect from this transmission level, some industry, and you can have independent IPPs, that is your independent power producers. So those also you can have here, or you can have them in the distribution system also. So so this was your unbundling of regular vertically integrated society. Now, when such type of system, or such type of arrangement of our power system was there it was seen that need of another entity, which we generally call as the ISO, or independent system operator. So what is the role of this independent system operator? Basically, it will let's say you have sellers, if you consider these are based nothing but sellers of your power. Here you have buyers of your power. So Let me add a slide. So let's say G1, G2, you have D1, D2, G3, G4, D3, D4, and this is hole in an area, and these are hole in another area, and this is your tie line. So let's say your G1 and D4, they want to buy and sell power. That is, G1 wants to sell power to D4 and D4 wants to buy power from G1. So for this transaction, for G1 to D4 transaction that we say, basically the what that will mean that the generator will inject some power which is required by D4, and D4 will basically take that power. But whenever there is such a type of transaction, so it will lead to change in power flow, right? And it may lead to voltage violations, because let's say it is injecting 100, generator G1 wants that 100 megawatt it wants to buy, and D4 wants to, sorry, G1 wants to sell, and D4 wants to buy. So we don't know that when this huge amount of power is injected, so it may so happen that there is some voltage violation in the system, or it may lead that there is some line thermal limit violation. Due to this, maybe this all adverse effect may be there uh, on the system. So who will take care of that? So that there comes the independent system operator. So it will take basically validate, or it will allow the transaction such that the system is in healthy condition, such that we can say there is no voltage or line limit or any other violation in the state of the system. Violation occur due to this transaction. So this is basically briefly the concept of ancillary service. So for that purpose, we need this independent system operator who will basically say yes or no. It will validate whether the transaction between this GenCos and DISCOs can happen or not. So if this 100 megawatt is not leading to any violation, it will say okay, it is good. You can have this contract between you. If let's say this 100 megawatt is leading to some unfavorable condition, let's say voltage is going above the threshold, then it will tell the G1 and D4 that no, this amount of transaction cannot happen, and you may decrease this 100 megawatt to 80 or 90, and then it will allow that transaction. So that is the role of the independent system operator in this vertical, in this unbundled or deregulated system that we say. So is this clear? Or if you have any doubt, you can unmute and ask. Okay, so after this, we have some participation metrics for this deregulated system and unit commitment. So that two topics we will discuss tomorrow. So tomorrow we have a extra session. So during that session, we will discuss those two topics, and after that, your like content for this week will be over. So we'll be discussing that tomorrow. Is it fine? So I will close the session for today.